Here's the solution to homework set number 13 for ECE 341, Random Processes. This homework looks at t-tests. The first problem is previously we wrote a Monte Carlo program to play random hands of poker. Using that, estimate the odds of getting a full house. So I set up the program to play 100,000 hands, or 10,000 hands of poker, and count how many times they get a full house. So as I run it, dealt out 10,000 hands, and of those 10,000 hands, 3 were 4 of a kind, 12 full houses, 223 of a kinds, and so on. The numbers that I care about are right here. So if I run it once, I don't really know much. To get meaningful data, I've got to run it a couple times. So here I ran it 5 different times. So the numbers I get are 12, 9, 21, 13, 12. From that, estimate the odds of getting a full house. Now, to do that, what you do is take your data, find the mean, find the standard deviation. Since I'm estimating the mean and the standard deviation, this is a t-distribution. So it kind of depends upon when you're talking about an individual or a population. If I want to know what is the actual average of getting a full house, that's the population. The more data I have, the more I know. So in that case, I divide by the square root of the sample size. So the probability of getting a third house will be roughly 13.4 out of 10,000 plus or minus 2.132 standard deviations. And where this comes from is this is from StatTrak. I've got 5% tails, and the t-score corresponding to 5% with 4 degrees of freedom is 2.132. So I'm going to go left and right, 2.132 deviations, and I get this. Now, if I just use the standard deviation of a full house, what this tells me is that next time I run the program, I'm going to get a number between 3.79 and 23, and that kind of makes sense. As I ran it, these numbers are between 3 and 23. On the other hand, if I want to know about the population, I'll take the standard deviation divided by the square root of the sample size. Because as the sample size goes up, I squeeze down and know more and more and more about what the actual mean is. So this says the actual mean is somewhere between 9 and 17, or the probability is between 0.09% and 0.17%. Based upon combinatorics and enumeration, the actual odds of getting a full house are 0.14%, which is in this range. So that kind of makes sense. Problem 2. This is real data from fall 2021. I taught embedded systems in person and online, and here's the class average for the in-person people versus the online people, mean, standard deviation, sample size. From that, test the hypothesis that in-person is better than online. Well, to do that, I need to set up a t-distribution. I'm going to create a variable w. That's the difference between a and b. So this is a minus b, which is w. It's got a mean. The mean is 7.34. And a standard deviation. What I want to do is find out what is the probability that w is greater than 0, which is a is greater than b. It's a funny looking b. This area. So I need to find the mean of w, the standard deviation of w. Again, if I'm looking at a population, I'll divide by the sample size. So this is the class average. What's the probability that the class average is higher? In that case, the standard deviation is 4.14. Degrees of freedom. A couple ways to calculate it. This is the exact way. There are 17.97 degrees of freedom. The simpler way, which gives you almost the same answer, is take the minimum of the degrees of freedom in A and B. That'd be 10. Find the t-score. That's x over s, 1.76. Go to a t-table and find out what is 1.76 given 18 degrees of freedom. And the probability is 94%. If I used 94%. If I use 10 degrees of freedom, it's also 94%. So the degrees of freedom don't really have a huge impact when you're up around these numbers. Basically, there's a 94% chance that the class average for in person is higher than the class average online. Now, a couple people didn't do the population, they did an individual, which is fine. If you do an individual, I don't divide by the sample size. And you get 66%. What that tells you, if you take a random person in person, a single random person online, 66% of the chance that the in-class person had a higher average. So, at least for me, it does appear that in-person is better than online. But online has other advantages too, like you can take the class whenever you want, you can have a job, have a life. But anyway, back to the ranch. Problem 3. If you go to this website, it will let you check your reflex time. For example, you do this. Bring it down so you can see the link. Start the game, wait for the light to turn green. When it does, I click the wait, or click the button. Do it a second time, wait for it to turn green. So you get your reaction times. I ran that using my dominant hand, both eyes open. Those are the times that I got. From that, find the 90% confidence interval for my reaction time. So given the data, find the mean, find the standard deviation. From StatTrak, 5% tails with 4 degrees of freedom corresponds to a t-score of 2.132. So we need to go left and right, 2.132 standard deviations, where this is the mean. Gives me between 0.23 and 0.308, which kind of makes sense. That's where the data lies. Problem 4, let's do a comparison to means test. Suppose instead of using my right hand, I use my left hand. What's the chance that my reaction time with my right hand is less than my reaction time with the left hand? Well, to answer that, I need to take some data with my left hand. It has a mean, standard deviation. Now, to use a t-test, again, the trick is create a new distribution W, where W is A minus B. The mean of W is the difference. The standard deviation of W is, since I'm doing populations here, the standard deviation divided by sample size. This is for population, saying that overall, is my right hand better than my left hand? An individual would just be a single test. If you want to do an individual, you don't divide by the sample size. That's for the variance. So my mean is at minus 0.0016. 0016. Yeah, pretty sloppy. Here's 0. I want to find out what is this area. This area is A is less than B. Reaction time is better. Find the t-score. T-score is 0.18, which says this area is 43%. So, actually, I did that wrong. This area is 43%. This area is 57%. So 57% chance that my dominant hand is better than my non-dominant hand, basically a wash. You know, I'm not ambidextrous, but this kind of says there's not a huge difference in the two. Problem 5. Close one eye. Now run the test. Is reaction time better or worse with one eye closed? So again, you repeat the experiment, collect some data, create a new variable W that's A minus C. When I did that, the mean is negative 0.02. I want to find out how much of the area is left of 0. So to do that, I find the standard deviation. And again, I'm going to look at the population. Am I better off with 2 eyes open or 1 eye open? Find the t-score. And this corresponds to an area of 6%. Or 1 minus that is 93.55%. So I'm 93% certain that my reaction time is better when I have 2 eyes open. 6% certain that I'm better off keeping 1 eye open. So basically it says that if I'm driving a car, I should probably keep 2 eyes open. Well, there's other reasons too, but reaction time is one of them. And that's homework set number 13. Again, kind of note, with a t-test, I just want to have a single variable. If you have two variables, change the problem. Turn the two variables into one by subtracting. And then I can find the difference between the two. That's homework set 13 for ECE 341.